Welcome to The Explainer. Today, we're digging into how AI makes really smart, educated guesses, using an incredible tool for reasoning when all the facts just aren't in yet. Think about it. From a doctor trying to figure out an illness to a bank deciding on a loan, we are constantly having to reason with incomplete information. It's just a fundamental part of life. And it turns out we can actually build a map for that whole reasoning process. All right, so here's the plan. We'll start with what this map of beliefs actually is. Then we'll look at two key ways of thinking with it, see what happens when things get really complex, and finally check out a real-world example. Okay, first things first. What exactly is this map I keep mentioning? How do you even begin to visualize the web of connections that shapes our beliefs about the world? Well, think of a Bayesian network as a kind of diagram showing how different things influence each other. It's basically a visual map of cause and effect. But here's the key. The connections represent probabilities, not rigid certainties. This is what allows a machine to think in shades of gray, which, let me tell you, is a major leap for AI. So check this out. You can literally see how these ideas connect. That arrow from smoking to lung cancer, that shows a causal link. And the one from lung cancer to the chest X-ray result, that shows how the disease can affect a test. It's just a super intuitive way to map out knowledge. And this is the crucial part, right? Inference is how we actually use the map. It's the engine that lets us take a new piece of information, like say a test result, and then update our beliefs about everything else in the network, like the chances of someone actually having a disease. Okay, so we've got our map. Now, how do we read it? Well, it turns out there are two fundamental ways to reason with it. Basically, two directions we can travel along its paths. First up, we have what's called predictive, or causal reasoning. This is top-down logic. We start with a known cause, and we try to predict the likely effects. We're looking forward in time. So, for example, let's say we learn that a person is a smoker. Boom. We've just been given evidence about a root cause. We can then use the network to push that information forward and calculate a new, updated probability of them getting lung cancer. Now, the second way is diagnostic reasoning, and it works completely in reverse. Here, we observe an effect, and we try to work backwards to figure out the most likely cause. This is bottom-up logic. And this slide shows that exact situation. If we see a positive X-ray, that's our observed effect, we can reason backwards along the arrows to update our belief about the probability that lung cancer is the underlying cause. So to put it all together, this slide really breaks it down. Predictive reasoning is all about forecasting forward from cause to effect. It's asking, what's likely to happen? Diagnostic reasoning, on the other hand, investigates backward from effect to cause, asking, what likely caused this? Okay, our simple lung cancer example is fantastic for getting our heads around the basics. But what happens when the map isn't so simple? What happens when it starts to reflect the true, messy complexity of the real world? In the real world, networks can look like this. Just take a second to look at that thing. The mentor system uses this massive, tangled web of variables, everything from a mother's age to a baby's birth weight, to help with medical diagnosis. Calculating probabilities here is a whole different beast. Because with that many interconnected variables, trying to find a perfect, exact probability can become, computationally impossible. The number of calculations just explodes, making it an intractable problem even for our most powerful supercomputers. So what do? We get clever. Instead of aiming for a perfect answer, we use some neat tricks to get a good enough estimate. Think of it like this. Direct sampling is like rolling the dice thousands of times to see what comes up most often. Likelihood weighting is a smarter way of rolling, where you only focus on the outcomes that actually matter based on the evidence you have. And MCMC, it's kind of like taking a random walk through all the possibilities to find the most likely spots. Now, let's bring all this theory back down to earth and see how it gets applied in a really high-stakes field, finance. How do banks decide who gets a loan? The key question for any lender is always, what's the risk? Well, Bayesian inference gives them a powerful way to calculate it by combining a whole bunch of different variables, like your age, your income, your past behavior, into a single probabilistic score. And as researchers in a 2023 study put it, carefully analyzing these probabilities is absolutely critical. Every single piece of information about a client shifts the odds, and the network helps put a precise number on that shift. And this table shows you exactly what that output looks like. Given a client's age and income, the network does its thing, it performs inference, and calculates the precise probability of them falling into different risk categories. You see that? There's a 45% chance they're a very low-risk borrower. That's not just a gut feeling, that's actionable intelligence. And all this leaves us with a pretty fascinating and maybe a little daunting question. As these maps of beliefs get better and better at modeling the world and reasoning with all its uncertainties, how much of our world, from medicine to finance to justice, are we going to ask them to predict and diagnose for us?